So construction begins with some blue variable resistors. You can see a couple of them. Also in the lower left-hand corner, the speaker, microphone, and key jacks. And in the upper right-hand corner, you can see the heat sink, which is on top of covering up three powertrain transistors. They're very small because this is a low-power radio. And then we move on to additional bits. Now we've added the RF gain and audio gain controls down at the bottom. You can see the shafts for them, no knobs yet. Also up above, we've got the power connectors, two kinds of them. The PS2 keyboard connector, and on the right-hand side, the orange box is a relay for changing the antenna over from transmitter to receiver circuit. Also, the BNC antenna connector is there, and empty filter board is there, also plugged into place. So all the headers for the filter boards have been installed. And last but not least, the LCD display has been installed. And that pretty much finishes up the kit, except for building the installing the capacitors and winding or soldering on the toroidal inductors for the on the filter board. And have to have at least one for testing purposes. So that pretty much wraps it up. This is the completed RFBitBanger. This is the main board, of course, and this is one of the filter boards. This is built for the 40-meter amateur radio band. Have to use a separate filter that plugs into the main board right here. These two sets of header pins for each of the different bands that you want to operate. There are 9 HF bands that we could build filters for, and was provided with enough materials came with the kit to build those. And I'll probably build at least a couple more, but we'll stick with the 40 meters for now. We have this thing hooked up by a coaxial cable, the output of the radio coming around here to this RF watt meter, so we can measure its output and see what sort of output we get, if anything. It's currently set so that it will show us the output that it would have without the filter installed, bypassing the filter. There's a jumper right here, that one bypass jumper and another bypass jumper for the filter is right here. And they're both installed now so that we can get full power out of this thing, see what its full power is without the filter, then put in the filter and see. But first I'm going to recreate what happened when I first powered this thing up. This is a 11-volt battery. We're going to plug it in here and see what I saw. And the very good thing that I saw was that no smoke came out of any of the components. And feeling around on the board, the output power transistors, there are 3 of them under this heat sink. They do not feel hot, and that's a good thing. But no display on the LCD readout here, and I luckily remembered not too long after I first powered it up that there is a variable resistor down here underneath the LCD readout that controls the contrast, and so there we go. That was all it took, and all of a sudden I've got my frequency displayed, which is 7.15 megahertz, right in the middle of the 40-meter amateur radio band. Now to transmit, I have to use these 5 push buttons here to make some adjustments here. They correspond to up and down arrows, these 2 ones that are arranged vertically on your keyboard, and left and right arrows like on your keyboard, and then enter. I don't happen to have a keyboard hooked up. It would connect to this PS2 connector here. You have to use a PS2 keyboard. But in the event that you don't have a keyboard with you, these push buttons will allow you to do everything you need to do. So I've already have the frequency set, so I'm going to put it into keying mode. I'm going to go up to look for keying. That's scanning, a fast scan if you want to scan the bands quickly, a slow scan. Transmit mode, that's by default is set at Morse CW for Morse code, so that's okay. And now I need to enter in keying, and it's going to ask me to remind me that I need to change the bandpass filter module if I've changed bands, and I'm just going to accept that. And now I should be able to transmit. Now there's a jack here for plugging in a Morse code key, but I don't have a Morse code key with me either. So in that event, the lower push button after we're in keying mode acts like a straight key. And when I push it, I should transmit. And then we should see something on the power meter here. So hopefully we'll see something. Press it, we're transmitting. The transmit light comes on there. And we can see that we're up to right about 3 watts, 3 watts output. Okay, so that's pretty good. This thing is designed for 4 watts output. And it's also, I believe, designed for up to 15 volts, and I'm sure that at the higher voltage, instead of this 11, basically 11 volt battery, we would probably be getting up around 4 watts output. Okay, so great. Now we need to put in the filter and see what effect that has. First I have to remove these jumpers that bypass the filter for when you're not using the filter. This one has to be not just removed, but moved over to a different position. There. Now it's going to include the filter instead of bypassing the filter. Then we have to put the filter in. So here's a filter. Make sure I've got it oriented correctly here. And double check to, I don't think that's quite right. There, that feels better. It went straight down in, and we're going to look down here and see if it looks like all the pins went in. Not missing any of the pins. Yeah, okay. So that looks good. Filter installed. And so we'll try transmitting again and see what happens to our output power. So push the lower push button, see the transmit light comes on, and we're down to a little bit below 1 watt. So we've lost a little over 2/3 of our power by using the filter. The FCC, of course, requires that you use the filter for ordinary purposes, but in case of emergency, you're allowed to bypass filters and transmit at full power, even though you're transmitting a dirty signal with lots of harmonics. In the case of an emergency, that's allowed. Okay, so what we need to do next is take a look at the characteristics of this filter. We'll hook it up to a vector network analyzer and see just how well the 2 parts of the filter are doing. This is really 2 filters connected to one another. There's the bandpass filter, which uses this toroid, which has more windings. It's resonant at a lower frequency because there's more windings, gives you more inductance and a lower resonant frequency. This is band pass filter for 40 meters. And then this is a band stop filter that's it's a parallel resonant, but it has fewer windings, and in fact it's resonant at the second harmonic of our transmitted signal. So that's at 14 megahertz. The most powerful harmonic is the second harmonic always, and of a radio signal for sure. And the purpose of this, the parallel resonant circuit, is to absorb all the energy that's at that frequency and squash that second harmonic. But so we'll hook it up to the vector network analyzer, the VNA, and see what's going on. Well, here we are looking at the Nano VNA, a vector network analyzer, a small one, so nano. These have gotten real small and pretty inexpensive, under $100. I can get them down around $50. And what it's going to do is it has a output port here that's going to inject a signal into a device, the device under test, the DUT, and then a return port here, and it's going to compare the signal strength of the input signal and the output signal, and tell us what the gain of the device is. And here in the case of a passive filter, it's going to be a negative gain. We're going to see a number of how many dB we've lost in terms of the power output as a result of going through the filter. And we're going to look at injecting frequencies in a range of frequencies. Here I have it set, the starting frequency is 1 megahertz and the ending frequency is 30 megahertz. That's the HF spectrum, part of the spectrum called the high frequency portion, and then plot dB loss against frequency. So I built a little jig here to connect the bandpass filter of the RFBitBanger up to the nano VNA, and so we'll do that now. And let's see, we've got don't have the pins plugged in here correctly. I'm going to put the phone down, sorry about that, the camera, and get it hooked up correctly. It's easy to get the plugs misaligned, the pins and the header pins that go into the filter. So there it is, and immediately we can get a result here. It has compared the output to the input signal strength at 401 different points. Okay, he can do as few as 100 points, and 400 is the most it can do, so it's picked 400 evenly spaced points between 1 megahertz and 30 megahertz and made that comparison and plotted it for us. We've got a marker here that we can move along with a stylus, and this, of course, this dip down in here is supposed to be the very well, let's see, we're down minus 54 decibels basically at that point. So we've lost 54 dB of our power output there, and that's happening at 13.8 megahertz. So that's pretty close to the 14 megahertz band, and that's not too bad. And then if we move this up, the very peak up here, where we have basically almost zero dB loss. Hopefully that's somewhere around the 40 meter band, and yeah, it's a little high. It's 8 megahertz, 8.3 megahertz. We'd like to get it down to closer to 7.5, or anyway, we'd like to when we're at somewhere near 7.5 megahertz, like this 7.45 megahertz, we would like this reading to be as close to zero as possible, as close to a 0 dB insertion loss. Here we have a little over 1 dB loss. Okay, and so that's what we're going to strive for, and I'm just going to see if we can get a little bit closer to that by adjusting the spacing of the turns on the two toroids here. The 40 meter toroid here, our frequency of resonance where we're letting the most signal through here is too high. It's at up around 8 megahertz. So we need to lower the frequency. That means we need more inductance in the filter circuit, and so one way we can get that is to squeeze these windings together closer. On the other hand, this point right here where we have our greatest loss of power, which is what we want to have happen right around 14.15 megahertz, right in the middle of the 20 meter band, it's actually occurring at 13 megahertz. So we need to get a higher frequency. That means we need less inductance, so we need to spread out the turns as far as we can. They're already spread out pretty well on this toroid, and see if we can get a better reading. So just to remember what we're getting here well, let's get this closer to 7.15 here and see what our reading is. I can also do that on a wheel that's up at the top here. So adjust it down. 14.162, that's pretty good. It's at minus 1.65 dB. We'd like to see how close we can get that to 0 dB at 7.162. So I'll try that first. I'm going to turn off the camera and come back with the result of having squished those windings together closer to see if we can get a little bit less loss in the middle of the 40-meter band. Well, I spent some time adjusting the windings, the spacing of the windings on the two toroids. Here for the 7 megahertz bandpass filter, I squeezed the windings together closer. Not good to squish them all the way together. That doesn't work well either. But so this spacing was the best I could do with the number of turns I have, and what it did was to drop us from a minus 1.65 decibel reading, or raise us up from that to a minus 1.3 decibel loss. Not that great, not that dramatic, probably not even worth doing. And then similarly with the 14 megahertz stop band filter, this thing spacing out the windings as far as I could, it really didn't have much effect at all. So what's going to happen is that I'm going to have to remove a winding or two from this toroid and add a winding or two to this toroid and then check them again. But they're actually not that bad. Only losing 1 dB at the middle of the 40-meter band, that doesn't account for losing 2/3 of my power. 2/3 of my power being lost there. I don't think it's due to insertion loss of this filter. It's got to be some other problem in my wiring of the circuitry, either leading up to or away from the filter, that's causing that kind of a loss. Because to drop from 3 watts down to 1 watt, that's not a 1 dB insertion loss. Yeah, I've got more work to do on getting the output power increased, though it does seem to be a working transceiver, just not at as high a power as it could be. So we'll see where future developments lead. And I can't leave this video without showing my post-apocalyptic 3D printed case for the RFBitBanger, which I ordered from Xometry. That includes just a top, a bottom, and some extensions for the push buttons that go through holes in the top. But they do work. Exit. And I ordered the cheapest possible mode of producing this thing, using the cheapest process, the cheapest plastic, and next available color for everything. So I did manage to get the same color for the top and the bottom. They're both black. Then the button extensions are white, which makes it easier to see them. And stuck on some labels here. I screwed up that one, got it misaligned, but oh well. At least I can remember, without having to try to read it off the circuit board, where to plug in the key, where to plug in the speaker to hear, or headphones in here. And I need some more labels. I need to label these. This is RF gain, this is audio gain, and then I need to label the power jack 12 to, or I think it's 9 to 15 volts, and then the PS2 keyboard jack, and also the antenna jack. But got the process started here, and it came pre-stressed with these diagonal scratch marks on it. Great, it's post-apocalyptic. One of the main ideas of the design of this radio was to have something simple that could be powered low power but using forward error correction, the GOLE code as one mode of transmission. Also, it'll do radio teletype and Morse code, and it will attempt to decode those things and display what it's seeing down here at the same time. We'll see. It'll be interesting to actually get this thing on the air at some point. I guess I could try it with 1 watt, which is what it's at right now, and see what happens.